Hey there, chemists. In this lesson, we're going to look at an introduction to what are called complex ions and coordination compounds. We're just going to look at how they form, what their equilibrium constants look like, and a little bit about the types of geometries that we see, which will remind us of some of the geometries we saw in the first semester of this class. A complex ion is formed when a metal cation is treated with some kind of polar molecule or anion. For example, the cobalt ion can combine with 6 water molecules and form a complex where the cobalt is covalently bonded in what's called a coordinate covalent bond to, in this case, 6 water molecules. The water molecules are neutral, so the cobalt's 3+ charge is maintained in the formula at the end. And here's a picture of what you could imagine it looking like, where these are water molecules surrounding the cobalt. So we've actually seen something like this in our acids bases unit when we looked at the hexa aqua aluminum ion. This is almost the same thing, just happens to be a cobalt ion. And you'll notice that it's the oxygens that are attached, forming bonds with the cobalt in the middle. So there's a few others. If I just drew the products of these, a single silver ion and 2 chloride ions would make silver with 2 chlorides and then an overall negative charge. This one has a charge with the anion that gets added, so 2 times -1 plus a +1 is an overall -1. A copper with 4 ammonias would be written as copper, parentheses, NH3, 4, and then a 2+ charge. And then an aluminum with 4 hydroxides would be written as aluminum, OH parentheses 4, and then a net -1 overall. These are written as equilibria, but they're actually very, very favorable to form the complex. At least the ones that we're going to look at have very large formation constants. We use a new subscript for the word formation, and it's called a Kf, but it's still just an equilibrium constant, and typically they're very, very large. 1.1 times 10 to the 33 is what it happens to be for this aluminate complex. And they're all aqueous. I'm not writing them with the AQ pair of letters in parentheses, but these are all aqueous species from aqueous ions and aqueous what are called ligands. You'll also notice something else about the complexes. Typically, but not always, usually the number of ligands is double the charge on the metal. That's not always the case. It actually depends on what the metal is and what charge it is. But for a rule of thumb, if we have to guess, something that has a 3+ charge will pick on 6 ligands. A +1 charge will take on 2, a +2 will take on 4, etc. And I specifically used this aluminum example to show that that's just not always the case. A +3, this aluminum is actually only taking on 4 hydroxides. And many times, multiple possible complexes exist. These are not the only ones, but what we're going to do is just look at what they look like and what types of geometries they have. To add some vocabulary words to your repertoire, the metal acts as what's called a Lewis acid. And that's an electron poor species. Any transition metals, and many post-transition metals like lead and tin can do this, and even aluminum, as we just saw. The ligand acts as what's called a Lewis base, and that just means it's electron rich, and it has to have lone pairs. It can be a molecule or an anion, but it has to have lone pairs attached to it. So here's just a list of molecules that are common ligands, and also some anions that act as common ligands. And all of these have lone pairs attached to them. The water molecule has a lone pair set on the oxygen. The ammonia has a lone pair on the nitrogen. The chloride certainly has lone pairs all around the chlorine atom. Even carbon monoxide, what we can call a carbonyl, can act as a ligand. There's lone pairs on both the carbon and the oxygen. There's two that I want to draw attention to that are called bidentate ligands. They're the two that are at the bottom of each column. The word bidentate, bidentate means it bites twice. It can actually bond twice. These bind twice. And the examples I want you to know are the oxalato ligand and the ethylene diamine ligand. And there's a picture of what each one looks like where we have the ligand, and here is the oxalato ligand. And if you look, that just is an oxalate anion. And both oxygens that have negative charges are forming covalent bonds with the copper. This happens also with the ethylene diamine. Here is an ethylene diamine molecule, and we see two spots where the same ligand form a bond. So it's one ligand that forms two bonds. We said that forms two coordination sites. It just attaches in two different spots. It's got two arms to form bonds with the same single metal center. So more terminology. Ligands form what are called coordinate covalent bonds in which all the electrons come from the ligand. So it's a shared pair of electrons, but the metal didn't donate anything. All the electrons came from the ligand itself. And we've only seen so far complex ions. These all have charges, but they act like any other ion, and you could pair them with another ion of opposite charge, and you get what's called a coordinated complex or a coordination compound. Coordination compound. And that happens when we just use one of these coordinate covalently bonded complex ions and pair it up with some other ion of opposite charge. So the copper ammonia complex could pair up with a sulfate. Their charges match, so it's just a 1-to-1, and you simply write it, cation followed by anion. This would be written as Cu, parentheses, NH3 close parentheses, and then an SO4. And they have a little bit fancier names. They're still named by cation followed by anion. You don't need to know how to name these for the purposes of this class, but they're named using the Greek prefixes, in this case tetra meaning four, because there's going to be four of the ligand. The ammonia group is called an amine with two M's. And this is a copper 2 complex. So the cation is called tetraamine copper 2. And then the anion is the one that you should already know from your polyatomic days. That's just a sulfate anion. So it's a much heavier name, but go ahead and try the other two. Don't worry about the names as much, but try the other two. Hit pause, and then see if you can write what the correct formula would be of the coordination compound by combining those ions together. Okay, the chromium complex. If I combined one of the chromium complexes with, they're already telling me, 3 of the chlorides, makes sense to make the charge neutral, I would write it as cation first, so Cr, parentheses, NH3, 6, and then Cl3. This would be called a hexaamine. Instead of tetra, it's 6 of them, so they use the prefix hexaamine. This is a chromium. The charge on the chromium is 3+, so I put a pair of Roman numerals as 3, and then the anion is chloride. So the naming sounds complicated, but it still is cation followed by anion. It's just a much more complicated cation. And then the last one, speaking of cation first, it's 3 potassium ions. So I write K3, and then Fe with 6 what are called cyano groups. So the name would be potassium, cation first. And then hexa for 6. Again, you don't need to know the nomenclature for this class, The CN group is called a cyano when it's a ligand. And the iron you can just call iron 3, or sometimes they'll use the more old-fashioned name of a ferrate. That also means iron 3. You might see both of those. So you will not need to know how to name complex ions. We will talk about the geometries of these complexes, and there's only a few that you need to know. Unlike all of the different molecular geometries we saw for small molecules, we're only going to focus on these four for coordination compounds. The simplest is when you have a metal cation making two coordinate covalent bonds with ligands, occupying two coordination sites. That is, as you've probably already guessed, described as a linear geometry. When you get to a four-coordinate system, when you have four bonds, there's actually two possibilities. The first one should be familiar. The first one is called a tetrahedral geometry, just like it would be if it was a small molecule. But there's another option that's in a plane, and that's called square planar, which might also be familiar if you think back to some of the more advanced molecular geometries we saw in the past. And then the last most common one is a 6-coordinate system. That's something occupying 6 coordination sites around a metal. This is called an octahedral arrangement. And remember, that's because if you connect all the atoms together in this arrangement, you get what's called an octahedral system. If you were to connect every single plane in here, you get a 8-sided figure that's called an octahedron. And at the bottom is just some common geometries that we see for specific metals and coordination numbers. You notice that some of them vary depending on what the coordination number is. We'll always have that to refer to it. So that's a short introduction to how complex ions work and how they form coordinated complexes.